Okay, so there's many ways to classify energy. This is just one of those ways. In this case, we're going to classify it as something called mechanical versus non-mechanical. So mechanical forms of energy. This has to do with things that have energy of motion, energy of position, either due to gravitational or elastic potential energy, and energy of motion. Non-mechanical could be things like heat. We have a pretty extreme form of non-mechanical energy right now in our classroom. It's so hot in here, we classify that kind of energy as non-mechanical. Non-mechanical could also be chemical potential energy. When you ate some food this morning, chemical potential energy would be considered non-mechanical. You probably have heard of like solar energy, sometimes called radiant energy, nuclear potential energy. These are forms of non-mechanical. So there's lots of energy forms. The ones that we're going to focus in on are the mechanical energy forms, which is kinetic energy, gravitational, and elastic energy. It has to do with very large moving objects. So objects that are large, that are moving, or stored energy that could cause those objects to move is what we call mechanical. Now, when I say large, I got to classify that. Large means bigger than atoms. So anything at the atomic level would be considered more like chemical potential energy or heat energy. It's associated with particles at the molecular level, sort of moving back and forth. Nuclear, the energy within a nucleus. So larger objects, throw baseballs around, you got a car driving down the road, those are what we consider mechanical in nature. So bigger than atoms. Now, the first form that we have to quantify is this thing called kinetic energy. The fact that objects are moving means that they have the ability to do work. So again, work is the means by which you transfer energy. If something's moving, it can do work. Raise your hand, you've ever seen these wind turbines going up US 31, going towards Ludington area, huge wind farm, 100 plus wind turbines. Those things are up there capturing the energy of the wind. And so as the wind turns those blades and does work, it transfers that energy into electricity, and we can store those or put those right onto the grid. An object's KE is equal to the amount of work it can do on something as it exerts force. So the fact that it has energy, it takes force to change that motion. Well, how much force does it exert while it's stopping? How we define kinetic energy? Again, we have a lot of ways of quantifying energy, and most of them have equations. So this energy equation is called KE, 1/2 mv squared, is how we would quantify an object's kinetic energy. I'm going to take just a moment and contrast kinetic energy with momentum. You might remember, let me write the momentum equation first. The first chapter or first unit had to deal with momentum, and it could be talking about how quickly momentum changed. Your egg drop devices, some of you determined the amount of force acting to stop your egg drop device by looking at changes in momentum. You might even remember this equation that we used. That was called the impulse momentum theorem, and we said, well, force was equal to the rate of change in momentum. Now, that stuff is dealing with momentum. You notice I have an M and a V. Well, kinetic energy has the M and V in it, but it's got a half in front, and it's got a V squared. So it uses the same physical properties of an object, mass and velocity. It's just a different way of talking about how much energy it has. Now, we're going to find, this is coming, that force is related to kinetic energy just like it was equal to momentum. You'll find that it's equal to this. And instead of me using a time as a quantity, this one uses a distance as a quantity. We're going to develop that equation. Okay, but I want you to see the comparisons between momentum and kinetic energy. They both have masses and velocities. Okay, so very similar kinds of things. Now, the biggest difference between momentum and velocity in kinetic energy is that the V is squared in this equation. So it has a mass, but this one has a mass, but it's got a velocity squared. Kinetic energy increases with the square of the speed. So what we mean by that is that the speed being squared in that equation makes that factor be much more important than in momentum. If you double your speed, that means you would quadruple your kinetic energy. So twice as fast, 4 times as much KE. If you triple your speed, triple means 3. 3 squared is 9. So we would say that your kinetic energy increases by a factor of 9 if you triple your speed. Raise your hand, you've been through a driver's training class. There's always a question on driver's training tests that says, if you can stop in a residential street traveling 25 miles per hour, if you can stop in 10 meters by applying your brakes, they say, well, what happens if you're going 75 miles per hour, so it's threefold faster? On the highway, how much more distance do you need? Well, you would need 9 times as far. And it has to do with the kinetic energy. Did you have a question, Dick? No? Okay. Stopping distance is proportional to KD. You need 4 times the distance to stop when traveling twice as fast. And it, again, it has to do with that speed being squared. Okay. Questions for me? Questions? Okay, let's keep going. So, folks, we have a few problems that we have to be able to solve, and so this is more mathy than stuff that we did in the first unit. It's probably more math in this unit than we did in the entire first unit there. So, kinetic energy. We have to be able to use this equation, use the appropriate units. Mass has to be in kilograms, speed should be in meters per second. Here we have a car, it's 1,200 kilograms, traveling up a hill, traveling at 10 meters per second. I'd like to calculate its kinetic energy. So KE is just 1/2 mv squared. I take half of the car's mass, so 1,200 kilograms, I'm going to divide that in half. And I have to take that speed of 10 meters per second, and I have to square that. Now, you can use a calculator for this if you like. I try to make the numbers be somewhat straightforward, where you don't need calculators. Powers of 10s are always easy to work with. 1/2 of 1,200 is 600. 10 squared is 100. So multiply those together, you get about 60,000 joules. Again, all of this stuff is going back to this concept of work. It takes energy it takes work to stop that car. If that car is moving at 60,000 joules of kinetic energy, you'd have to take that energy away by doing negative 60,000 joules of work to stop it. That'd probably come from the brakes of your car. If you can't stop with the brakes of your car and you crash into another car to stop that car, that car would do negative 60,000 joules of work to stop it. A cheetah, fastest land animal, traveling about 60 miles per hour, short distances, 27 meters per second. How much kinetic energy does it have? I'd use the exact same equation, just with different masses and different speeds. This one I cannot do in my head. Use easier numbers there. So 75 divided at half, multiply that by 27 squared, and that gives me about 27,337.5 joules. The kinetic energy of that cheetah is just a little bit less than half the kinetic energy of that car. And again, the reason for that being so big is that 27 is squared, so it's a big factor. Now, one more question for you, number 3. Here I have 75 kilogram runners, so they're just out for a jog. And there's a number of them. My question would be, how many of these runners would I need to have so that the combined kinetic energy of those runners was the same as that single cheetah? You notice the masses are the same, 75 kilograms for each object. The cheetah, 75, the person, 75. I would like to know how many people we need to have the same kinetic energy. I'm going to ask you to try that whatever way you think you'd like to try it. And I'll show you a simple way after you're done. Right? Give that a shot. See if you can do that. How many runners would I need to have the same kinetic energy as a single cheetah? Okay. There are some approaches that you could take here to be able to determine the number of runners, and I'm wondering if anyone would be willing to share how you did it. But the records show that no one is raising their hand right now. Olivia, thank you. How would you do this?
I got 9 because if you multiply the 3 meters per second to get the same as the 27 meters per second, you have to multiply it by 9.
Okay, I love how you're using what we'd call proportional reasoning. Let me try that. So what Olivia is noticing is that I gave the same mass of the runner as the cheetah. So the masses are the same. But the difference in speeds, what Olivia said, is that the cheetah is traveling 27 meters per second and the runners are 3 meters per second. She said 9 times faster. But because speed is squared in that equation, the kinetic energy of the cheetah compared to one runner, the kinetic energy is not 9 times greater. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. How many times more kinetic energy does a cheetah have than a single runner? 81. So I would need 81 runners to be able to do that. There would be 81. So 9 squared is 81. I would need 81 runners for the same kinetic energy, for the same KE as the cheetah. You see how that 9 turned into an 81? It's perfect. Now some people might look at that and say, well, let me just determine the kinetic energy of a runner. Take 1/2 75 times 3 squared. And then take that 27,337 divided by that number, you get 81. This is using what we call proportional reasoning. Proportional reasoning means I don't even need a calculator. Just 81. All right, how fast would you have to throw a baseball? And I use this example a lot, right? So it is baseball season as well. Do you guys know it's going to be the Dodgers and the Yankees, right, in the World Series? So when a person throws a baseball, they're doing work on it. They're exerting a force through a distance. Same thing with a bowling ball. So they have different masses. The question would be, is how fast would I have to throw this baseball for it to have the same kinetic energy as a standard bowling ball? I want to see if you're able to do that one. This, again, is also somewhat mathy. See if you can do that one there. So a bowling ball, 67 joules. I want to know how fast I'd have to throw that baseball. Give it a shot. I didn't talk at all during that time. I just sort of wrote up that work for you. I don't know if you're able to do that math or not. That's a little bit more algebra than we've had to do in the first 7 weeks of this class. So I took the 146 grams and converted that into kilograms. I have to make sure I'm using standard units. So, and I set that equal to 67 joules. I went through, did that math, and I get about 30.3 meters per second. For those of you that play baseball or understand baseball, that's about a 68 mile per hour pitch. Is that doable? Can a pitcher throw a ball at about 68 miles per hour? Yeah, that's really not that bad. High school level, certainly be able to do that. So 68 miles per hour, the same amount of kinetic energy as a standard bowling ball. All right. So folks, a little bit of math there on kinetic energy. We have to be able to quantify that using that equation. Any questions before we turn the page? Questions before we turn the page? All right, then let's look at this next one here. And again, folks, I have to do a lot in a short amount of time because we have so little time before we go on our small break. Are you ready? All right, let's look at the second form of mechanical energy. So this is what we call potential energy. So kinetic energy is just energy of motion. This is potential energy. It's due to position. So I often highlight the PO of those words to recognize that potential is positional energy. It's energy stored within a system. So anytime we talk about potential energy, there's a system of objects involved. It can be considered stored. So energy that is potential is stored. Can be recovered. As an object has the ability to do work, which is a transfer of energy as its position changes. So we can store energy as potential energy and get that back. Gravitational potential energy, we abbreviate it as GPE. It's a common form of potential energy. It belongs to a system. Usually it's an object. And let's try this. Would you guys agree that this baseball has energy associated with this position? If I drop it from here, it can do some work on that table. If I drop it from higher up, would you agree it's doing more work? The object or the system is the ball, and what else that gives this thing energy? Gravity is not an object, though. Thank you for trying. That's okay. The system is the ball and something else. Not the table, thank you. It's not. The ball and something else gives this thing energy. Thank you. A lot of people would say it's the hand. It's not the hand. It's the system is the ball and the earth. So the fact that the earth is pulling on this means that it takes work to lift this thing up. If it wasn't for the earth pulling on this, it wouldn't take any energy to lift this. So it's the earth and the ball that give this thing energy. Questions for me? Questions in the back? All right. The amount of work that we do to lift an object in a gravity field is what we define as a gravitational potential energy. We go back to our concept of work. And so work is our transfer of energy. It's the stuff that we've been talking about since day one of this unit. If I define work as force times distance, I'm going to use color coding to help this make more sense. Force times distance, the force that I exert as I lift an object is equal to its weight. So F is equal to m times g. That's the weight of an object. And instead of us using a d, we're going to use an h. H just represents how high I'm lifting it. So the equation for gravitational potential energy is that GPE is equal to m times g times h. Take the mass of an object, take the acceleration due to gravity. So what is the value of g that this thing is in? And then how high do I lift it? That's how we define gravitational potential energy. But if you would lift this here so that you're not missing additional stuff. Okay. Notice that mass, again, is measured in kilograms. G is in newtons per kilogram or meters per second squared. H has to be measured in meters. And so, again, I see that energy is associated with the mass of an object. So I go back to any of these other equations that we've been looking at. I see that there's masses involved. I go back to the momentum equation. There's masses involved. And I go back to the gravitational potential energy equation. There's masses there. So mass is an important property of an object. I want to take and solve a few problems with you on gravitational potential energy. And then I'm going to stop and give you guys the remaining time to try some problems related to this. Wrecking ball, 125 kilograms is 4 meters above the surface of the earth. A little bit higher than this room. How much GPE does the ball have between exists between the ball and the Earth's surface? So again, I go back to my GPE equation. I simply take that 125 kilograms, that's the mass, Here on Earth, G is about 10 newtons per kilogram. So on Earth, that thing has a certain gravitational field. So I put in 10 for that. And it's 4 meters up. I put those numbers together, I get 5,000 joules. How much energy that thing has due to the fact that it's 4 meters above the surface of the Earth. Now, if I cut this cable, so the cable is cut and that ball crashes down to the Earth, it's going to do work on the Earth and it's going to leave a crater in the Earth. How much work it could do would be 5,000 joules. So as this thing crashes down and leaves a hole on that Earth, the amount of work it does is equal to its gravitational potential energy it had at that height. That's why we call that gravitational potential energy. It's how much work it takes to lift it. It's how much work I can get back when it falls back down. Carlos, student of mine from probably about 2011. So when I wrote this slide, I used him as an example here. He was a book reader. And he said he had a bookshelf in his room, so I gave a problem like this. 6 books for Carlos's bookshelf, each weigh 17 newtons. How much GPE do those books have relative to the 2.3 meters from the ground? So I'm going to, again, calculate that using gravitational potential energy equation. GPE equal to M times G times H. I see I have 6 books, so I'm going to put that out front. This 17, you guys recognize that 17 newtons is not the mass of the book, but the 17 newtons is the weight? I can tell that because the N is there. It's not those are not kilograms, those are newtons. So that M times G is 17. I do not have to multiply that 17 by 10 here. So 17 newtons is the weight. I've already got that G in there. And then I'm 2.3 meters up. So now I can go ahead and multiply those numbers out. So 6 times 17 times 2.3. And this is giving me about 235 joules. Now Carlos, great kid, but he is somewhat of a, I don't want to use the term slob, but he was messy. So he would always have his books scattered throughout the room on the ground. He would say that his mother would tell him, Carlos, pick those books up and put them on the bookshelf. My question for you is this. How much work would it take for Carlos to take those 6 books, 17 newtons each, and lift those things up to that bookshelf and put them on that shelf? How much work would be required? 235 joules. That's what we mean by that number. It's talking about how much work it takes to change its position. That energy is stored. We can get it back. Carlos explained once that there was an earthquake where he lived. And the earthquake took those 6 books and they knocked them off the shelf down to the ground. And they hit one of its connect structures. You guys know what a connect structure is. How much work could those books do when they fall off those bookshelves and land on the ground hitting that connect sculpture? How much work could they do? That much work, 235 joules. That's what we mean by gravitational potential energy. All right, this is your ticket to start these problems. I want to give you some time to be able to work on these problems. So I want you to show me that you can calculate how high up this diver must be on a platform so that when he falls from that platform down to the water below, he does 2,300 joules of work on that water. Right? So he falls from there, hits that water, does 2,300 joules of work. How high up? You try that. will you circle your answer? I want to walk around and see how you guys did. Yep, circle your answer. Good. I'm just walking around and want to see where we are with it. Yep, people are working. People are working. Pun intended. There you go. You go. But no, I'll still be your part. You guys won't be. I see some good F times D here. Anyone get it? I see some good F times D. I see some good work there. Thank you. All right, I will be here all week. The height that I'm seeing is about 4.1 meters. That looks right. And let me show you how I would do that. GPE is equal to mgh. In this case, I'm setting that equal to 2,300 joules. I'm looking for height, so I'm going to divide that 2,300 joules by mg. In this case, that 2,300 joules is divided by 56 kilograms, but there I have to multiply that by 10 because that 56 kilograms is a mass, not a weight. And when I go through and do that, I get a height of about 4.1 meters. And so that would be the height from which that person must fall from that platform to do that much work on the water. Okay? There we go. Now, folks, I went through that quickly. And that's, again, because we're somewhat pressed for time. So I want to give you guys a couple of practice problems related to kinetic energy and gravitational potential energy. You have over 10 minutes, which is more than I had for my first hour. You guys, 9:29, I'm going to ask that you get this done before you leave today. That way you are done with this. If you don't finish it, I would ask that you try your best to finish it outside of class, but you have the 10 minutes now. There's only 8 questions, so you can get this done, or at least pretty close to it. It's going to be Thursday, and so I'm rushing to get this done before we go on our fall break. That 2 days that we had, 2 days of like unplanned absence is sort of making us rush here a little bit, and I apologize for that, but give yourself a go at these, see what you can do. Please use this time wisely. Ignore the 97,000 or 970,090. That happens to be the number of copies that I've made in my tenure here at Grand Haven. That is a lot of copies. I've been doing this for a long time. And so, my gosh. Yeah, at least I think that's what that number is. Somehow I got put in there. Okay, so folks, again, I apologize for that being somewhat quickly done. 8 questions. Give that a shot. See what you can do. Use this time wisely. All right, I'm going to stop the video recording.